What's up? I'm live. I'm live for some more LeetCode. Um, Hold on, let me just fix this. You can't see my browser window yet. Aha! But now you can. Okay. So welcome. I'm back for more live coding challenge solving. I had a 2-day break. I've been streaming quite a lot on this channel, so I think it made sense. But yeah, I was not feeling mentally up to streaming the last 2 days, and today I am, so I'm back. Okay, what else was I gonna say? Yeah, short stream today. Unfortunately, it's probably gonna be about 2 hours long. It's probably gonna be a little less, honestly, just based on the exact start time of 12:07 p.m. PST. So I'm gonna have to get off a little bit before 2 o'clock because I've got an event that I'm going to. But I'm gonna try to solve some LeetCode problems in the time that I do have. And yeah, unfortunately, because it's a short stream, I'm gonna skip the Clash of Code section. So if you want to play Clash of Code, come back tomorrow, and I'll start the stream off with some Clash of Code. But yeah, today there's not going to be any Clash of Code, unfortunately. So yeah, I'm just going to jump straight to LeetCode. So let me update my stream title. And let's just review where we're at with LeetCode. So I'm going through the dynamic programming study plan. So let me show you that. The dynamic programming study. So you go to LeetCode, you go to problems, and then it's right here. There's 4 levels. I'm still on level 1. And so last time we solved ugly number, and we struggled a little bit with the linear time solution, but we got it solved in log n time, I guess, ish, pretty easily using a heap. But I'm gonna go back today, and I'm just gonna quickly code up the linear time solution. And then unique binary search trees we also solved, but we solved it using a formula that I found online for calculating the nth Catalan number. So that's probably the best solution to this problem, but I want to solve it with DP as well, because that's kind of what the spirit of this study plan is about. So I'm going to try to get through both. I'll definitely get through ugly number, and then I'm going to try to get through binary search trees. And then once we do that, then I'm going to start immediately on day 12, where it looks like they give you a little bit of a break because they throw 2 easy problems in the mix, Pascal's triangle and Pascal's triangle 2. So I hope to get to those today as well. And then last but not least, I just came across this problem called Alien Dictionary. It's LeetCode 269. And I'm quite fascinated by this. And looking at the submissions, I can see that I solved it in June of 2020. So hopefully I'll be able to go back today or tomorrow whenever I get to this problem and solve it again. So this one is probably the biggest maybe of the problems I talked about. I'm not sure if I'm going to be able to get to this one, but I will get to it, just maybe not today. Let me just add, I was going to add it to my bookmarks, but I see that it's already in there. Oh no, it's not in there. Okay, we'll add it to the bookmarks. Okay, so starting with LeetCode 264, ugly number, number 2. So here's the question. Let me just take a note of this somewhere else. When I'm solving LeetCode problems, should I just put the title of the problem in my stream title? Hold on a sec. Where is it that I'm keeping notes on? Shit for the stream. Do I have a place like that? Oh yeah, I do, right here. Let's see. Problem current problem title in stream title. Like I can find a way to automate that. And then it would also be cool if I could have a command, chat command that shows a link to the current problem. Chat command for link. So this is not going to happen like immediately, but I've been keeping notes on things that could be cool to do for the stream coming up in the future. So let me just put those in there. And okay, so I've got that. All right, so back to this problem. I'm back. So this is my heap solution, which does get accepted, but the runtime is slow. So I'm going to try to solve this again right now using DP. I already know how to do it. I'll try to explain what's happening along the way though. Okay. So the first thing we need is, well, we'll get our int n. Oh wait, we already, I'm stupid. Okay, so we need our vector of int dp. Oh no, it's, so that's actually, what our vector is we're generating the ugly numbers in order. That's how this works. And we're just pushing them onto the end. So we start off our vector int ugly, and it starts off with size 1, with 1 as the only value, and that's because 1 is the first ugly number. And then we're going to progressively generate more ugly numbers by multiplying the numbers that we already have by 2, 3, or 5. So because of that, we actually need 3 pointers. We need 3 indices. And the indices are going to correspond to the elements of the ugly number array. Oh, you sometimes zoom in. Oh, Gigantic Bucket, thanks for coming in. I haven't seen you for 2 days, but that's my fault because I didn't stream. And if I had, you probably would have come in. So apparently that would be useful. Okay, well, I took note of it. So I've actually been doing some stuff on the side, not live on stream. Some stuff working towards like custom Twitch integrations, like completely similar stuff to what like Stream Elements and Stream Labs lets you do. But, you know, as a software developer, I'm getting more satisfaction out of building a lot of the same functionality from scratch. But because it's from scratch, you know, I'm not locked into their constraints, you know, so I can basically do whatever the hell I want. So I've been doing some of that stuff, learning like the Twitch API and stuff. And yeah, so I've been taking notes. Yeah, the Twitch API is cool. So the thing about the Twitch API that I don't like is for chatbots, the way that you have to connect to like a chat room. It uses IRC, or like a WebSocket flavor of IRC. And instead of giving you like a, you know, an object containing all the details about a message that someone sent in the chat room, they send you this string that you have to parse. Here, let me send you a link. And they give you an example like parser. They're like, here, you could, whoops. So let's see, Twitch developer API chatbots, something like that. So here we go, parsing messages. So somewhere they have a link to like an example. Here we go, the example message parser. So they give you this, and they basically, the idea is you can copy and paste this into your code. But they say like this supports most of Twitch's chat message types, but not all. So you have to go in and actually like change this if you want to like be able to parse all the message types. Yeah, so that's actually a good point too. I want to find some libraries that will maybe do this for me, but I didn't go looking for it yet. So you said, yeah, you use libraries that abstract the IRC stuff away. If you want to throw down some links for stuff that you recommend that I look at to that end, I'll definitely bookmark them and take a look, because yeah, if there's an easier way to write a Twitch chatbot than directly connecting to their like WebSocket server and parsing messages manually, then I'm interested in that. Okay, so we have our 3 pointers, which is the pointer for 2, the pointer for 3, and the pointer for 5. And the pointers correspond to the index of the ugly number array that should be multiplied by 5 next, or multiplied by 3 next, or multiplied by 2 next. So you've got I2 equals 0, I3 equals 0, and I5 equals 0. But I don't know if I was aware that you've been writing Twitch integrations. That's cool. Like maybe at some point we could do some sort of collaboration. Because I'm like planning on like getting really into the whole streaming ecosystem, both as a streamer and as a developer. I've been spending a lot of time like learning the APIs and stuff. Yeah, so this is right. So now all we have to do is while our ugly.size is less than n, we continue and we find, while we don't have the nth ugly number, we find the next ugly number. That's what that while loop is going to do. And then once we're done, we just return ugly number of n minus 1. And then finding the next ugly number is just a matter of figuring out the minimum of multiplying the elements of these 3 pointers by what the pointers represent, 2, 3, and 5. So basically we're just going to have int next ugly number is the min. It's going to be the min of 3 things, so we got to do the min of the min. The min of ugly sub I2 times 2 ugly sub I3 times 3 and ugly sub I5. Yo, dude, gigantic bucket. That raid the other day was insane, right? I was super hyped about that. I didn't expect anyone to drop 60 viewers into the channel. So I don't doubt anyone from his community is here right now, but big shout out to Midnight Simon for doing that. I would raid him back, but at this point I don't ever have enough viewers to make that worth it. For JS, there's TM. Oh yeah, I'm gonna take a look at all these. Let me just open these in a different browser window. So we got TM.js, JavaScript package for Twitch chat. This looks pretty good. So you just give it your username and your password, and you tell it the channels that you want to join, and then it just gives you an on message. And then is message the only event that you listen for? Because I remember when you're writing the raw bot, you have to listen for like pings and notifies and priv message, which is what in this case it gets translated into the message event. How hard is it to reply? Oh, this is better though. Oh, you can connect anonymously? I didn't even know you could connect anonymously. CMI doesn't have the rest of the API service, just chat. I see. Well, that might be all I need for now. I'll either, yeah, I don't know. I'm not entirely sure yet if I'm going to migrate to a library, but I'll think about it. Oh yeah. So Twerple has API chat, event sub, and pub sub, which is nice because I'm gonna need most, if not all of those. The API chat. I was looking at Twitch's pub sub. It's pretty cool. I wish you could just use pub sub for chat though. You know what I mean? Like if they're gonna give you an API that's a pub sub API, Why can I not subscribe to chat messages? Like, why do I have to connect to an IRC for that? That's just me. That's just what I think. But and then the last one you sent me was Twitch lib. Okay, so you can read chat anonymously. That's good to know. Do you know anything about like rate limits with regards to reading chat? Because in the API docs, there were like rate limits for bots sending messages, which makes sense. And then they had a way to get your bot verified, and if you do, they would increase your rate limit significantly and stuff like that. But what about like listening? Like, are you allowed to just listen into as many chat rooms as you want? Oh, oh yeah, I was trying to remember if you get notifications for people joining and leaving the chat room or not. Okay, so let me just get back to this because I am on a tight schedule today. So we get our next ugly number. So that we know that that's the next ugly number, so we can just push it straight into the array. But then the outstanding question is, what do we do to update the pointers? Next ugly number. And that part I remember how to do as well. You update any of the pointers that generated whatever the next ugly number was. So if, for example, if ugly of I2 times 2 equals the ugly number that we just generated, then we increment that pointer. And then we just do this for all three. And that's because it's possible for, and this is, we talked about this for a while the other day, but it's possible and quite probable, in fact guaranteed, but at any iteration it's possible and probable that multiple of these pointers will actually produce the same next ugly number. And so when that happens, they all have to be incremented. So you do that. Skim chats at scale? Yeah, me neither. So if your library doesn't explicitly support anonymous, you can use any account named Justin Fan followed by 5 pound signs. Tech W. What? So how do you do the anonymous with the IRC? Also, are we good on this? Submit. Okay, there we go. So that actually that increases or decreases our running time by a lot. By going from n log n to n running time, we went from 200 milliseconds down to 13. Oh, you picked numbers. Yeah, it's cool. It's a cool solution. I wish I could have come up with it on my own, but that's fine. So the next problem is unique binary search trees. Also, I'm representing major coffee chains today, apparently. This is decaf though, because you know I'm kind of a wimp when it comes to caffeine. So I got my decaf Starbucks today for the stream. So if you, let's see, connecting to the IRC server. So you've got it must be as simple as, if you're not going to send messages, it must be as simple as you just don't give it the username and password, right? And then you can just say join a channel, and it probably just lets you do it, right? That's what I would assume. Anyway, I'll look at that more later. Oh, yeah. For this one? Dynamic programming versus intelligent loop. I guess this is dynamic programming, but dynamic programming doesn't usually use multiple pointers, right? That's where I feel like this kind of deviates from what you would generally consider to be dynamic programming. Like, this is kind of like dynamic programming plus 3 pointers mixed together, because you are reusing information that you've already generated. You're using the ugly numbers that you already know of, but you don't actually know which index you need. Like, you don't know which one to use without having this 3 pointers keeping track of it. Okay, so now I'm gonna see if I can figure this one out without just pasting in a formula for Catalan numbers. So how would this work? That's what I'm trying to figure out. So also, I'm trying to decide if I need to... Oh, yeah, you like my drawing from the other night? So I'm trying to decide if I need to update to like a paid software for drawing, or if I should just keep using Excalidraw. Excalidraw is awesome. But there's this one, actually, when I went to Midnight Simon's stream yesterday, he was using Epic Pen, which was the first time I'd ever heard of that. And I went and looked at it, and it looks good. It's nice because you can like draw over top of anything. Like, I could just be on LeetCode, you know, and I could start drawing like right here. That's cool. But I don't know, I like Excalidraw, and I like how it's in the browser, you know, I don't have to download software to do it. So if you got a binary tree of size, hold on, let me get some circles going here. Of size 1. And you got a binary tree of size 2, could be like this, or like this. Binary tree of size 3 could be like this, or it could be like this, or it could be like this. Those are not all the options for a binary tree of size 3 though. It could also be like this. And the other version of that, which is... This is getting confusing. Is that all the options? So you've got... Boop. Boop. What we're trying to figure out right now is, if we know the solution for I, how can we, in constant time, get the solution for I plus 1? Like, how do we relate those two? And I can't imagine it being that simple if there's literally a formula that does that. You know, the Catalan number formula. So if we have 1, then we can obviously like take a node and put it on the left as the left child. We can take a node and put it as the right child. If we're trying to figure out the answer for I equals 3, or n equals 3, then we're basically, so I think the idea is that we're adding a node, right? And so then we can take all the structures that we got in I minus 1, and we can take all of those structures, we can put them as the left child, and we can put them as the right child. So we, at the very least, we know that dp of I is equal to dp of I times 2. Or sorry, dp of I minus 1 times 2. But what else? Because it's not just that. But that gets us all this though, right? So I can take this tree, and I can put it as the left child, so I get this. But I could also put it as the right child, which gets me this. And I can take this subtree and put it as the left child, which gets me this, and the right child, which gets me this. So doing dp of I equals dp of I minus 1 times 2 handles these 4 cases. But then this case also though, this would be the case where you just take the new node and you take the two... Oh, this would be, you take the new node and you make it like the right child of this, or the left child of this one. Like these cases right here are when you take the new node and you make it the root of the new tree. So let's put a box around this, and this right here can be represented as dp of I equals dp of I minus 1 times 2. But then this part, and this is like, this is make the new node the root. So that now we just have to figure this out. So if we're not making the new node the root, then we're making the new node a child of one of the nodes in any of the trees for I minus 1. But the problem is, in doing so, you're gonna end up with duplicates, right? So if I were to put the new node here, that's the same thing as putting the new node here, but those are structurally identical, and so we need to only count that once. And additionally, like, let's say that we were trying to figure out dp of I equals 4, dp of 4. We could put the new node here, or we could put the new node here, or we could put the new node here. So how do we dedupe that in the math? That's what I'm trying to figure out. How do we dedupe that in the math? So if we're not making the new node the root, not making the new node the root. What are the options for where it could go? It could be a leaf. Well, if if we're not making it the root, then there's n-1 places that it could be a child of, and for those n-1 places, it could be the left or the right child, but it couldn't be like any of those though, because some of those are already filled. I feel like this is not the right way to think about it. Wait, is it? It's not just this though, right? There's no way it's just +1 right there. Okay, I think what might help is if I look at one more case. Let's look at the case of dp of 4 for n equals 4 or I equals 4. Let's have a peek. That might help me figure out what to do here. So for 4, well, first of all, you're going to take all of these right here, and you're going to make them the left and the right children of the new root. So you're going to have... Shit, I think I'm just going to draw these circles. I don't want to use the circle tool. So you're going to have that. You're going to have that. You're going to have... Hold on, let's take a look. Okay. You're going to have that. So these are actually the exact... That was lucky that I did it this way. This is these exact 4, but as the left child of the new root. So you got that. So you got all those, and then you got another 4 of the same, but except you're now the right child. So you got that. You got that. Then you've got this one, just a ladder. And then you've got this. So that's your dp of I is at least dp of I minus 1 times 2. You add a new node and you take everything from the previous, and you just make it the left and the right child of the new node. So we know dp of 4 is at least 8. What are we missing here? We're missing, okay, so the only thing that we're missing, and I'm pretty sure all of these are structurally unique. I don't think we need to dedupe anything here. Because, yeah, we know that because these are structurally unique. And if we take these and we make them the left and the right child of a new node, those are guaranteed to be structurally unique too. So we got that. And then so for this one, this is a case where, so we could take our new node and add it into, so we could have, let's see. We could have, okay, so we've got this. Let's just draw these 4 out again real quick. We've got that one. This one. Yeah, and then this one. And so let's figure out where the new node could go with a different color. So it could obviously go here. It could go here. Now it could not go here because that's not structurally unique from this. So it doesn't go on the bottom level. It has to be either, it can't be a child of a leaf, basically. So we got those two. For this one, it could go here. Or it could go here. for this one, it could go here, and it could go here. Are these all structurally unique? Because that's going to make this problem really easy to solve. It could go here, or it could go here. So this is another 8 possibilities. Are any of these mirrors of each other? What about, so how do I handle that with this one though? Like this one, the idea here is that to get from dp of 2 to dp of 3, like we could put a node here, but for this one we could put a node here. And the problem is that we can't count both of those because that's a duplicate. Those are not structurally unique. So why does that not show up in dp of 4? It's kind of hard to see. I'm trying to figure out if any of these are duplicates. I'm not going to draw all of these out though. So we have 8 options up here for dp of 4, and then this right here is another 8. Oh wait, no, we do have duplicates. We do have duplicates. This one and this one both have one that looks like this. Right? They also, oh okay, there's more duplicates. They also both have one that looks like this. Oops. So both of those, oh, and then I would assume that this, yeah, it's the same. So so over here, these two, they both have one that looks like this. Is that right? No, that's not right. I did just see it though. Yeah. So they both have one that looks like this. Yeah. Are those the only duplicates? So what are we looking at right now? So we know dp, let's get our formula being built here. dp of I is equal to dp of I minus 1 times 2 plus, here we have another 8. So this is, but in general, what is it though? It's the number of nodes it's the basically like all the nodes that can have children. Can't be any leaf nodes. We're never making the new node a leaf of the tree. We're either making it the root, or we're making it a left or a right child of something that's not a leaf. Um, son of a bitch. What time is it? Okay, still got some time. DP. These are the dupes that we found in here. For example, that. Oh wait. Wait, this is wrong. This one right here is not a dupe. So you can get it that way, but you cannot yet. I'm glad I noticed that. There's only two things that we need to dedupe, and it's these two. It's the case where, oh wait, I might be onto something here. The only dupes are where you make the new node a left or a right child of a non-root node. There's definitely some pattern going on here. Like, whenever you create a structure, like this, I think you need to dedupe, right? Because both of them have that. And that also corresponds to what happened here, where we created that structure. But how do we represent that in the math, though? Like, we're trying to condense all of these observations down to a formula, and that's the hard part here. So here, this is bothering me. Let me just go ahead and make this a little taller. So what are we looking at here? So we know that we need to subtract out 2. So here we're subtracting out 1. Here we're subtracting out 2. Is it the case that in general we're subtracting out two to the n minus 2? Wait. Are we subtracting out minus 1? So for dp of, this is for dp of 4. So it'll be 2 to the third. Well, we're only subtracting out 2 for this. And for dp of 3, we're subtracting out 1. So it's either we're just subtracting out like n minus 2, or we're subtracting out 2 to the something. Like, the question is, once we go to dp of 5, are we subtracting out 4 things, or 3 things? Or are we subtracting out 4 things? Also, once we get to dp of 5, we have this that we need to make sure that we represent. I like drawing binary trees. Can you tell? Well, what I don't enjoy is not being able to figure out the formula. So we've got we know for sure that we've got dp of I minus 1 times 2. What else do we have? dp of I minus 1 times, there's a whole bunch of possibilities here. The number of possibilities specifically is, the number of possibilities is going to be dp of I minus 1 for all of these, but then times the number of non-leaf nodes that have available edges. How do we even figure that out? You know, I'm going to be so annoyed with myself once I read the answer, because it's going to be like, think about it slightly differently, and then it's going to be like a really simple formula, and I'm going to be mad because I didn't think of it. Maybe we should just go back to Pascal's triangle, man, if we can't figure this out. Number of levels. Oh, this is gonna be, hold on a sec, let's just look at the code for a second. Not that we have any code, but this is not gonna be, I feel like because of the nature of this problem, it's going to be one of those where you have to add dp of I to the answer on each iteration. So it's going to be something like, this will be something, so we know we're going to have at least a times 2 here, but this is not finished. And then this is going to be answer plus equals dp of I. And so this is not actually the unique binary search trees with I nodes, because if it was, then dp of n minus 1 would be the answer. I think we're supposed to reformulate this a little bit. Let's see, maybe that makes the solution easier. Okay, this is not the proper way to solve the problem. I literally just like tried to put some math in here and see if I could get it to produce the right answer. So dp of I is going to be Okay, so here's another important thing to point out that I just thought of that I don't think I'm representing in my solution, or the solution that I'm working towards, which is that let's say that we get to dp of 7, right? We get to dp of 7. We need to make sure that our answer includes this. So what this is you can think of this as we need to make sure our answer includes things like this. So for dp of 7, we can take all of the dp of 3's, put them on the left child, and we can take all the dp of 3's and put them as the right child. So wait, does this have to be n squared then? For every I, do I need to iterate through everything I've calculated so far? And like put them on the left side and on the right side? So for dp of 7, let's try to think about this. For dp of 7, I can put, so for dp of 7, I have 6 nodes left. So I could have like, I could do like, I'm trying to figure out how to like write this. I could have like nodes with unique configurations of 1 and 5, and then also like that reversed as well. 2 and 4, right? And then that those could also be reversed, and then 3 and 3. And those could, well, no, those could not be reversed. No, those could be reversed and it would still be structurally unique. So for dp of 7, do I need to iterate? Do I need to iterate j? J goes from 0 to 7. No, 0 to 6. Well, we do like, so if we're doing a for loop, we'll have less than, so we'll do 7, and then it'll include 6. And then I'm iterating through all those, where j is the number of nodes I'm putting on the right subtree, and then it would be 6, it would be, you know, it would be like I minus j minus 1 nodes on the right subtree. And then I would have to like grab all those dp of i's. So the problem with that is now our solution is not linear, our solution is n squared. But does it need to be? Is there a way to do it in linear time? So if I look at my other solution, which was Python 3, this right here is, what's the runtime of the Catalan number approach? Oh, wait, you know what? It doesn't matter. I don't even know why I need to look at that. N is only 19. So since n can only go up to 19, n squared, n cubed, like all of that is actually fine for this. Okay, maybe I'll try to do it this way. So if I try to do it this way, then dp of I, then the changes that I made here in the code, I will revert. Do you remember what the changes were? Yeah, it does. I wasn't sure if it was going to remember across me switching to a different language. dp of I is the unique BSTs with I nodes. And then when alright, fuck it, let's just do it. Let's just try to code it up real quick and see what happens. So let's start off all of these at 0. dp of 0 is 1. And so now we're going with I from 1 up to n. And then within that, we're going to go j is... we want to put nodes on the left and right subtrees. It might actually be easier if we do this as an n+1. Might make it a little bit easier to think about, I think. So we start off with I equals 2. And so now I'm trying to figure out, so j is going to be, j starts off at 1. No, j starts off at 0. 0 nodes on the left subtree, all the nodes on the right subtree. Yeah, that's right. Then j is less than I. Yeah, that's correct. Because we have one node as the root, so that means in this case, there's only one node to go as the left or the right child. And then j plus j. So j is the nodes on the left subtree. K is going to be the number of nodes on the right subtree. So k is going to be I minus j minus 1. Does that work? Yeah, I think that's right. So then dp of I plus equals dp of j hold on, let's think about this. So I'm going to take all of the nodes from all the different configurations in the left subtree could be matched up with all the different configurations for the right subtree, which would mean that it has to be dp of j times dp of k. Is that right? Let's just run this. Oh, dp. Okay. And then what else? Plus something, right? Let's go back and look here. Uh, Okay, let's have a look at the array. So we can just set a breakpoint here and use the debugger. So we got 1, 0, 1. What was the expected output? What's the test case? Oh, n equals 3. Okay, so the answer is supposed to be 5, so obviously we're way off. Okay, the number, so, hold on a minute. The number of structurally unique binary search trees with 0 nodes is 1, because you just have no nodes, and that's the only one. So is that part of the problem? Okay, so that gets me correct output for that sample test case. Luckily, we can test to see this, how good this is, how right this is, just by testing the max test case right away. We can also test 0 and 1. So let's check all these cases. Yeah, I am doing 19. Does it want me to do less than 19? Oh, okay, it's the 0 that's not right. They tell you that they won't give you 0. Okay. Oh shit, we're right. That's it. That's the solution. So I spent a while thinking about it the wrong way. All you gotta do, so hold on, let me just submit, but I'm pretty sure we're right if we're getting the right answer for test case 9, the 19 test case. So if we submit, we get it accepted in 2 milliseconds, which means that the n² runtime is probably optimal, but I will look at the solution page and verify that. But let's just draw out what I did. Although I already drew it out, I'll just review it. So the solution is basically none of this stuff that I talked about here, although I did have to go through this process to get to the solution. The solution is that if you're trying to figure out dp of I, then what you do is, if you're trying to figure out dp of I and you already have all of the previous dp's, dp of I is number unique BSTs with I nodes. Now, when you're calculating dp of I, we've already calculated dp of 1 or dp of 0, whatever, all the way up to dp of I minus 1. So when you go to dp of I, you're basically taking all of the trees that you've already looked at, all the unique trees, and you're adding one new node to it. So the way that you formulate the problem is that you take the new node and you just make it the parent. You make it the root of the tree, because every tree has to have a root. So we just go ahead and we formulate our problem such that whenever we're looking at dp of I, we're going to take node I, the brand new node, and we're going to make it the parent. So we can just do it like this. We can make a little dp of I. Now, if dp of I is the parent, then we're going to have some sort of subtree on the left side, and we're going to have some sort of subtree on the right side. Now, the subtree on the left side could have 0 nodes, which means the subtree on the right side has to have I minus 1 nodes, right? Alternatively, the subtree on the left side could have 1 node, and the subtree on the right side would have to have I minus 2 nodes. And so the solution, the n² time solution, is just to iterate through all these possibilities of, in my code, I called the number of nodes in the left subtree j. So go through all the possibilities of having j nodes in the left subtree, and then it ends up being I minus j minus 1 to get the number of nodes in the right subtree. And so you iterate through all those, you get all the unique, basically you get all the pairs, right? You're going to get 0 and I minus 1, you're going to get 1 and I minus 2, you'll get 2 and I minus 3, and then it'll go all the way until you have you have it flipped, right? You're going to go all the way until you have I minus 1 on the left and 0 on the right. And then for each of those, you know the DP for that. You know how many structurally unique binary search trees you have for that count. So you multiply it together, right? You get a little multiplication, because any of the configurations on the right side could be matched up with any of the configurations for the left side. I had that backwards, sorry, left and right side. So you multiply to figure out the unique matches, the unique number of matches. And so when you code that up, exactly as I just explained it, you end up with this code. So you have a couple of base cases. The number of binary search trees with 0 nodes is 1. The number of binary search trees with 1 node is 1. And then you can just start off at 2, and you can go up to n. And then for each new node, J iterates through the number of nodes in the subtree on the left. And then we can use I at J then to calculate the number of nodes in the subtree on the right. And then we increase dp of I, because dp of I has to take into account all of these. We increase it by the product of dp of J and dp of K, and then that gets you the answer. Pog, that's the DP solution. Well, that's a DP solution for unique binary search trees. Now that we got that, and I'm very pleased, let's go ahead and look at the solution suggested by LeetCode. So approach 1 is dynamic programming. Yeah, this looks like what we did here. So G of n is the number of unique binary search trees for a sequence of length n. F of I in n is the number of unique binary search trees where the number I is served as the root. Okay. G of n is the desired function we need in order to solve the problem. Later we would see that G of n can be deduced from Fin, which at the end would recursively refers to G of n. Yeah. Yeah, so deep in our case, DP, the DP array is G of n. And then our for loop is iterating through all the f of INs. So yeah, here's the code. This is exactly what we did. Time complexity is n squared. So that's what we did. That's good enough. That would definitely be good enough in an interview. It's good enough in a coding contest, most likely. I suppose it's possible that a coding contest might want you to do better than that. But then approach 2, mathematical deduction. So this is what my first approach was, and that was just because the only reason I was able to do this is because I was already happened to be familiar with what Catalan numbers are. And in this problem, Catalan numbers happen to solve the problem. So if you know Catalan numbers and you can recognize that a problem reduces to the sequence of Catalan numbers, then you can just paste in like the formula, or if you have like some code saved somewhere, or you can find code on the internet, you can just get it. So here's the formula for Catalan numbers. And yeah, so then they have just some code where they could, code it up. And so for Catalan numbers, you get a linear time complexity. And actually, I think that's better than I think that's a little bit better than the Catalan numbers that I pasted in, because my Catalan numbers, no, mine might be linear. Because mine is recursion and memoization, so I think it probably ends up being linear as well. The runtime was 20 milliseconds, but I think that's just because it's Python 3. If I were to code up the same solution in C++, I think it would be fine. Okay, so that's it for LeetCode 96, unique binary search trees. Next, we're going to move on to what I'm expecting to be fairly straightforward dynamic programming problems, straight from the dynamic programming study plan on LeetCode. We have Pascal's triangle. And then after that, we have Pascal's triangle too. I'm not sure what the difference is, but we'll find out. And I'm going to solve these after I just take a quick, I believe, 5 minutes or so break, and then I'll be back to do a little bit more dynamic programming. So, be right back.
Target acquired. Target acquired.
Okay, I'm back. Okay, now I'm back. Let's go. All right, so let's look at Pascal's triangle. Given an integer num rows, return the first num rows of Pascal's triangle. Each number is the sum. Okay, yeah. So this one's extremely straightforward. Vector of int, I don't know, PT for Pascal's triangle. We'll start it off with size 1, with 1 as the only element. And let's do a do while loop. Don't get to write do while loops very often, but we'll see if we can make it work for this problem. Yeah. We'll have our vector of vector. So it wants a vector of ints, so that's actually going to be the PT, my bad. So we'll have our vector of int current with 1R. So do while. First thing we're going to do is pt.pushback cur. Pretty sure that's going to push back a copy. So now we're free to take cur and turn it into the next one. So yeah, we're always gonna have ones on the sides. What's a nice sneaky way to code this up? For yeah, and then the while loop can just be while pt dot size is less than num rows, and then at the end we just return our pt. So I is 0. I is going to be less than current dot length. Sorry, current dot size. So basically, this loop will iterate for the number of new elements that we need in the array, and we're just going to be pushing back. It might actually be. We could keep track. Okay, how about this? We keep track of but like back 1 and back 2. Back 1. No, this would be back 2 and back 1. And back 1 is going to be 2 ones. Yeah. PT needs to start out by having both of those in it. So pt dot push back 2. And then back 1. Okay, yeah, this looks good. The only thing is they might ask for like 1 or 2. If they ask for 1 or 2, then we have to so let's call num rows n. They want, yeah. It's not really, n's good enough for that. So if n equals 1, return Pascal's triangle. If n equals 2, return Pascal's triangle. Now we know n is greater than 2. We can come into the do while loop and we can do the business. So the first thing we do is not that. First thing we do is next. And let's iterate through back 1.size. Trying to think about what's going to be a nice way to do this. Next, we can just start it off with a 1 in there. Oh, what is cur.back1? That's not a thing. Back 1. I don't know if we need back 2. We might just need back 1. Yeah, I think that's totally right. We don't need to keep track of 2 of them. So let's update the code to that effect. We just need a prev and a next. And then after that, I think we can just push back a 1 and then prev equals next and pt dot pushback next here. So now what we're doing is we're doing all the sums now. So next dot pushback prev of I plus prev of I minus 1. Yeah, that's why I did back 1 and back 2, was because row 3 is the first row where you have the numbers that you need to sum. So we'll do it this way. We'll still just have prev. So prev equals 1 1 pt dot pushback prev. If n is 1, we return it. Then prev dot pushback 1. If n is 2, we were yeah, we need this. Next starts off at 1 1, and now we can do prev of I plus prev of I plus 1 onto the next array. Oh no, because prev. Wait, no, it's right. Is that right? Okay, that looks good for 5. Let's try the largest test case, 30. Okay, yeah, we got it right. So this is how you can do it. You just take care of the first 2 rows kind of manually outside the loop, and then the third row is when you can when you actually like start summing. Another way to do it would have been, I can just draw this real quick. Like you can pad the triangle with zeros too, and then you can just do the same sums without having to worry about going out of bounds. So if your Pascal's triangle is like 1, 1, 1, I'm going to draw it as a right triangle because that's how it's going to look like in an array. 1, 2, 1, you know, 1, 3, 3, 1, where the sums are going, you know, this way and this way. One way to do it would be to have like zeros here. So then for this one, you can do the same sum like that. And then this one would need to be, yeah, we need a 0 here too. So basically, you keep zeros on either side of it, and then this is the only like special case. You still have to initialize the first row to 1, but you don't have to. Your code doesn't have to handle the first 2 rows manually, whereas my solution does use the first 2, does do the first 2 rows manually. Yeah, and this looks right. And then so whenever you're creating your next row, you just start it with a 1, end it with a 1. Again, if you do the 0 padding thing, you don't have to do this, because you'll just be summing 1 with a 0, and it'll work automatically. I'm not doing that, so I need to handle these 2 cases specifically. And then you then do the sums for whatever's in the middle, where you're referencing the previous row. So let's submit that. We get that one accepted. I mean, it's linear time, linear on like the number of rows. No, I mean, I guess you'd say it's n squared, right? Because the row length is also increasing at a rate of n. Yeah, time complexity is num rows squared. There probably isn't a better way. There's definitely not. I think the way you can argue that there's no more optimal time than num rows squared is that your answer is going to be on the order of num rows squared. So just to generate the answer, you're going to have to do at least num rows squared of work. Okay, so that's it for Pascal's triangle number 1. Let's take a look at the next one, which is Pascal's triangle 2. What did they add? Given an integer row index, return the row indexed row of the Pascal's triangle. So I think the point that they're trying to get across with this is if you don't need to generate the whole triangle and return it, you can be more space efficient. And you can generate the row indexed, like you can generate the nth row using only linear space. But it's still going to take n squared time. So let's just call this n, and what I'm actually going to do here is to save some time. I'll copy my code from the previous problem, and I'll reuse parts of it. So yeah, if I just paste this in, I don't need PT anymore, but I do need an integer I to keep track of what row we're on. So we don't need no PT. So I'm just going to remove PT entirely from the solution. And we want to get to the point where we can just return prev down here. So we start off our Pascal's triangle with 1, 1. If n is 1, we can just return return it. Prev doesn't feel like a great variable name. Let's just call it row, since they're trying to get us to return a specific row. So let's just rename prev to row. So if n is 1, we return row. Then we push back another 1 onto our row. If n is 2, we can return row. Then we go into a do while loop where we're making the next row. We're iterating through the previous row to do sums. And then row equals next. And now the thing that we need to do is so we could use an I counter that counts up to n. That would probably be fine. So n equals 2, right? Start off, well, no, not n, sorry. I equals 2. And then every time we generate a row, we can increase I. And we keep going until I is equal to n. So this the return value for the problem is now just vector of int. And this right here is return row. Okay, and so they renamed, this is now just get row instead of generate, because I copied my code in, so I overwrote like what the function that they want us to write is called. Okay, and so we're off by 1. So for I equals 3, 1, 1, 1, 1, 2, 1. Oh, sorry, they want the 0 indexed row. So I would actually just be 1 here. Yeah, so that works. We can submit that and it will be accepted. Oh, it's possible for them to ask for index 0 in this problem, which wasn't possible in the previous one. So wait. Let's get that custom test case in here, 33. Okay, so now it's good. Okay, so that solves it, but so I mean, it's just so quick, 5 milliseconds. Whenever you get problems running that fast, like usually the numbers that they have up here are not worth paying much attention to. Like if I submit a few more times, we're gonna get a range. So that time it ran in 0 milliseconds. So that's the point I was trying to make, is that this is like time optimal. It doesn't look like it's space optimal, but it's still space linear though. Like we're not building the entire triangle, we're building one row at a time. If you wanted to be like max space efficient, you could probably do it without the creation of a new array. But yeah. So then the other thing that you could do here that I think I'm just going to do for fun is you don't have to create a new counter variable I. You can just do while n here. So if this would be if n minus minus return row, then this would be if n minus minus return row. Get rid of this. So now what we're going to do is we're just counting down n. And then this is so n. So yeah, actually it's going to be easier to do plus plus n and treat n as a the number of rows to make, not the 0 indexed row. So then we can do if minus minus n. If minus minus n. And then this would be while this would be while so if they give you 1, so this needs to be like not minus minus n. So we need to decrement it, and then if it's 0, and then I think the same here. So let's think about this. If they ask, so for the case of 3, they want the 4th row, so we put it at 4. If we could decrement it and it's 0, we want to return the row. So for example, if n was 1, so if they give you 1, that means they want index 2. So we increment it. Hold on a sec. Is this where I want to figure out like where this starts to fail? So let's ask for 0, 1, 2, 3. Let's just do that. So we're right up to, okay, so our code works until the loop. So until n is greater than 1. So as soon as n becomes 2, so we return the row. This is, so if n were 3, then here n becomes 4, then here n becomes 3, here n becomes 2. We get down here, n is 1. So we do the work. No, sorry. If they ask for index 2, n is 3, then 2, then 1. Oh, this is, okay, this is just normal minus minus n. Okay, yeah, that's it. So this refactoring makes my code less readable, but it makes it more memory efficient by a factor of 1 integer. 1 32-bit integer. So let's just submit that and get it. Oh, my memory usage, and look at that. So I went from 6.6 megabytes to 6.4 megabytes, and now I'm using less memory than 80% of C++ submissions. Let's go ahead and look at the solution. It's going to be pretty straightforward. Dynamic programming. Memory efficient dynamic programming. Let's see how they did it. So they have a, yeah. So this is what I was saying is if you structure the DP in a nice way, you don't have to use an extra vector. So they have their answer starting off at row index +1. And, oh, okay, I see. So they start off their answer array as the final length of the array. They're not pushing back anything, basically. That's smart. And they fill it with ones. Then, since they're filling it with ones, they just have to sum. Oh, and they can, I see, they can wipe out. They're not wiping out, they're just summing answer of j minus 1. Oh yeah, so they go through each row and then they go through all the numbers. Answer of j plus equals answer of j minus 1. I see, that's clever. That's kind of what I wanted to do, but smart. Math. Approach 4. Combinatorics. Oh, yeah, that's true. I forgot about this, but there's a formula for calculating the nth row of the Pascal triangle. And I think it's, binomial coefficients. So, and then that increases your time complexity to linear. So up till now, everything's been quadratic time. But then if you know the math, n choose r is n factorial divided by r factorial over n minus r factorial. Then you can calculate basically you can calculate the elements of like the ith row of Pascal's triangle, because those are equal to binomial coefficients. So n choose r equals n minus 1 choose r minus 1 plus n minus 1 choose r. And if you notice, those two terms are the two numbers directly above the number n choose r in the triangle. This recurrence is the same as the intuition for approach 1. While knowing Pascal's rule does not give us any benefits over previous approaches, knowing that the numbers in the triangle are just binomial coefficients will come in handy. Successive binomial coefficients differ by a factor of n minus r plus 1 over r. Oh, so if you know the factor of the consecutive coefficients, you can just use that. So they start off their answer as an empty vector just containing 1. And then they're just iterating to calculate they're iterating to calculate the rest of the row, and then it's just a formula. So basically you can just calculate the row in you can calculate the elements of the row in constant time. So it's the previous elements of the row times n minus k plus 1. So yeah, it's math. Further thoughts. The symmetry of a row allows us to get away with computing just half of each row. True. Pop quiz. Are there any computational complexity benefits of doing this? Pop quiz. Can you prove why the rows are symmetrical? I mean, I probably couldn't prove it mathematically. But I could prove it like loosely, just by looking at the recurrence relationship. This Stack Overflow answer has a good explanation. See the parallel between time complexity, recurrence, and Pascal's rule. Starting with C++11, standard move can be used to move resources across arguments or references. Since underlying representations are moved and not copied, this can be a very efficient operation to transfer elements across. Well, I need to learn more about that for sure. Let's just open this up. So just looking at the time right now, Pascal's triangle will be my last solve of the day. I'm going to come back tomorrow, hopefully for a longer stream, and do start off with some Clash of Code for probably like at least an hour or two, and then go into LeetCode. I might start trying to do more binary search as well. So binary, yeah, I might actually like replace Code Wars, which was historically as in like the past week or so been a part of the stream. I might start doing Clash of Code, binary search, and LeetCode as the main segments of the stream, because binary search is pretty cool. And you can do like little mini contests. So if members of the chat want to do little mini contests, then we can do so on binary search. I did get that idea from Midnight Simon because I watched his stream yesterday and it was awesome. He's a great streamer. And yeah, it seemed like people really enjoyed using binary search as a way to do like little contests just between Simon and members of the chat. So well, maybe I'll start looking into doing some more of that stuff here. And yeah, so just looking at the time, I'll look at standard move on my own time later. So I'll just bookmark that. Tomorrow I'll definitely do Alien Dictionary. It seems like a pretty interesting problem. So there'll be that coming up tomorrow as well. Hopefully some more Excalidraw like this. And yeah, so that's it. I've got to go get ready to leave. I'm going to get some food. A prearranged appointment. So with that, I hope everyone who was here has a great day or evening or night or morning, whatever time it is for you. Thanks for stopping by, and I'll catch you on the flip side. Hopefully I'll see you tomorrow. Peace.